Good afternoon, students. Today we will be starting about the medicinal chemistry 6th semester, the first unit, where we have discussed about the first chapters like the beta-lactam antibiotics, cephalosporin, aminoglycoside. Now we have came to the antibiotic, that is the tetracycline. So tetracycline is coming under one type of antibiotic that is containing tetra, means four cyclic ring, that you can see from the structure A, B, C, D, whereas four rings are there. So, and they are cyclic in nature. That's why it is known as the tetracycline. So, one by one, I will be going to discuss the slides. So, we have discussed about the classification of the drug, about the mechanism of action. So, how the tetracyclines are working. So, first of all, we should know the chemistry of the drug. Among the most important broad-spectrum antibiotic are members of the tetracycline family. Nine such compounds like the drugs coming under this: tetracycline, rolitetracycline, oxytetracycline, chlorotetracycline, democlocycline, meclocycline, methaqualin, doxycycline, one of the most important, have been introduced into medicinal use. Several other process antibiotic activity also. The tetracycline are obtained by the fermentation procedures from the Streptomyces species or by chemical transformation of the natural products. That means they are generally derived from the bacteria and from the fermentation process. Or sometimes, if they are not available from the fermentation of the bacterial sources, they can be produced in the synthesis process also. Next, the stereochemistry of the tetracycline is very complex. You can see from the structure. So the starting from the nomenclature, you can see from the 1, 2, 3, 4. The fusion will be known as a 4A, 5, again the fusion 5A, 6, again it has 6A, and 7, 8, 9, 10, 11, 12. And the fusion will be given as a 11A and the 12A. And alternatingly, there will be a double bond O, that is a chiral group, oxy group, and at the 11 alternate position, the oxy group will be there, and the 12 and 10 position, hydroxy group will be there, OH, OH. And there are some OH group in the 12 position also. At the fourth position, N-dimethyl group is present, and at the 5 position and 6 position, at the 5 position and the 6 position, there are, and the 7th position, there are some substitution can be there. So the first, starting from 7th, it is known as R1, and the 6th position, two configuration or two substitution will be there, R2 and R3. At the 5th position, R4 will be there. So in case of R2 and R3, one of the substitution will be below the plane and above the plane. Okay, so there is presence of another CONH2 group and the hydroxy group at the second and third position also. So depending upon the substitution, oxytetracycline and doxytetracycline, each with 5 alpha hydroxyl substitution. So in this position, doxycycline and oxytetracycline, the 5 alpha hydroxycarbon will be substituted with the OH group and have 6 asymmetric centers. So others lacking chirality at the C5 have only 5. So that means the drugs will be having 6 asymmetric centers. As a result, different isomers will be forming. The others lacking chirality at the C5 have only 5 isomers. Next, among the most important broad spectrum antibiotic, it is one of the important category. Now, structure of the tetracycline. So I have shown you the R1 and R2 and R3 here. R1, R2 and R3 and R4, depending upon the position of the change R1, R2 and R3 and R4, the tetracyclines are given different type of name like tetracycline, chlorotetracycline, oxytetracycline, democlocycline, methacycline, doxycycline, minocycline, like this. So depending upon the structure activity relationship, different drug will be different property also. The stereochemistry of the tetracycline I have discussed here. Now, the tetracycline are amphoteric compounds forming salts with either acids or base because they contain the CONH ring. And in neutral solution, these substances exist mainly as deuterions. That means both have positive and negative ions. The unusual structural grouping in the tetracycline produces the acidity, 3 acidity constants in aqueous solution of the acid salts. See, in this position, the yellow box. For this CONH group, there is a pK. For these 3 rings, and there are some hydroxyl and oxygen group, that's a pK2. And for the NHCH3 dimethyl amino group, there is a pK3. So the This groupings of the tetracycline produces three acidity constants in aqueous solution of the acidic salts. So that's why different type of acidic salts can be produced. So strong acid and strong base attack tetracycline with the hydroxyl group, the C6, causing a loss of activity through modification of the C ring. That means in the C6 position, like we have started the numbering from this position, 1, 2, 3, 4, 4A, 5, 5 with 6 position. So the sixth position hydroxyl group can be attacked by the strong acid and base, loss in the activity through the modification of the serine. As a result, the activity sometimes is lost. Strong acid produces dehydration through a reaction involving 6 hydroxyl group and 5 alpha hydrogen. So strong acid sometimes it produces the dehydration, that means the water removal through a reaction involving 6 hydroxyl group and 5 alpha hydrogen. That means at the 6th position hydroxyl group and the 5 position hydrogen will be removed as water. So that double bond thus formed between position 5A and 6 induces a shift in the position of the double bond between C11 and C12 and up to a position between C11 and C11a, forming the more energetically favored resonant system of the naphthalene group found in the inactive and tetracyclines. That means that I'm showing the structure. So C5, 5A, 6, 6, 7, 8, 9, 10, 11 in this position. If the structures are double bond is shifted, so as a result, it forms a more energetic drug. So like this, at the sixth position as the 6 alpha position, the acid and strong acid having a strong attack. At the 6 hydroxyl base is also promote a very attack, and the ketone group at the 11th position causing the bond between the 11 and 11A atoms to cleavage the ring. And just 1 second. To cleave the ring and found in the inactive isotetracycline. Thus, two unfavorable reactions stimulated research that lead to the development of the more stable and longer acting compounds 6-deoxytetracycline, metacycline, deoxycycline, and minocycline. So, as a result, they form different type of structures of different tetracycline, deoxytetracycline, metacycline, and doxycycline, like this. So, see the base and acid attack. If the base is attacked, so there is another group formation at this position, and if the acid is attacked, then some changes are going on. The ring can be cleaved. See, the ring is broken down here. Okay. Okay. So as a result, if the acid is breaking down the ring, so subchelate complexes are formed by the tetracycline with many metals, including calcium, magnesium, and iron. Such chelates are usually very insoluble in water, accounting for the impaired absorption of most, if not at all, tetracycline in the presence of milk, calcium, magnesium, and aluminum containing antacid and iron salts. So soluble alkalizers such as potassium bicarbonate also decrease the GI absorption of the tetracycline. Like if sodium bicarbonate is reacted with the compound and the salt is formed, so then it will decrease the gastrointestinal tract absorption. Okay. The affinity of the tetracycline for calcium causes them to be incorporated into newly forming bonds and teeth of tetracycline calcium orthophosphate complex. So if the calcium is reacted with the tetracycline, so it forms some problem to the bones and teeth. That's why tetracycline should not be given with the milk. That means whenever you are taking any tetracycline, milk cannot be consumed. That's why it may make a problem. They will form a complex and they will make some corrosions or them some staining of the teeth and bones also. There will be some bleaching of the bones. Mechanism of action, I'm just giving a very short description. Tetracycline are very specific inhibitor of the bacterial protein synthesis. They bind to the 30th ribosomal subunit and they thereby prevent the binding of amino acid tRNA to the mRNA ribosomal complex. That means whenever the tRNA and the mRNA is attached with the different DNA or the translation process is going on, so the 30th ribosome plays an important role for carrying the mRNA and tRNA. So if the drug is attached with the ribosomal subunit, then the mRNA and tRNA cannot be incorporated and they will not form the particular protein. As a result, the protein synthesis will be inhibited and the structure of the bacteria will be destroyed. So, three biochemically distinct mechanisms of resistance to tetracycline have been described in bacteria. So, that is not to be discussed and as a large. I'm going to the next slide. Now, spectrum of the activity. So, the tetracycline have the broadest spectrum of the activity as the one of the antibacterial agent. They are active against a wide range of gram-positive and gram-negative bacteria like spirochetes, mycoplasma, rickettsiae, and chlamydiae. And resistance to tetracycline among the both gram-positive and gram-negative bacteria is relatively common. That means they are having a broad spectrum activity, but sometimes some of the bacteria get also resistant with this antibiotic also. Now coming to the structure activity relationship, there are numerous points, but we will be highlighting to the most important points. So all derivative containing fewer than 4 rings are inactive or nearly inactive. That means the 4 rings here present in the tetracycline is most important for the activity of the drug. If the 4 rings are substituted with a lower number of rings, then the activity of the drug will be decreased. The simplest tetracycline derivative that retains the characteristic broad spectrum activity associated with this antibiotic class is 6-dimethyl 6-deoxytetracyclines. That means at the 6th position, if the 6th position is methylated or deoxytetracycline is there, that means one oxygen will be removed at the 6th position. So then it will having a broad spectrum activity. The enolized tricarbonyl methane. Enolized tricarbonyl methane system with C1 and C3. You can see the C1 and the C3. If the enol group is attached here, is very good, intact for very good activity. Next, replacement of the amide at the C2 position. At the C2 position, if the amide group is replaced with other function, that is aldehyde nitrate, and reduces or abolishes activity. That means CONH2 group is very essential for the antibiotic property. So monoalkylation of the amide nitrogen reduces activity. That means amide nitrogen here, if there is monoalkylation, if one alkyl group is introduced, then it also reduces the activity proportional to the size of the alkyl group. That means if the alkyl group is having larger size, then the activity will be reduced. That means you always remember, if the chain or alkyl group's length is increased, the activity will be decreased. That means smaller alkyl group will have more activity. The dimethyl amino group at the 4th position, see 1, 2, 3, 4. 4th position, the dimethyl amino NCH3 NCH3, that is also discussed in the faster structures, must have the alpha orientation. That means above the below the plane, and 4-epitetracycline are much less active than the natural isomers. So the structure should have the alpha orientation, and if 4 position, if the 4 position epitetracyclines are present, then it will be less active, natural isomers. Removal of the 4-dimethyl amino group reduces activity even further. That means if the amino groups are removed from this 4th position, it will reduce the activity also. That means N-dimethyl group is very essential for the activity. Activity is largely retained in the primary and N-methyl secondary amines, but rapidly diminishes in the higher alkylates. That is already discussed. The N-methyl, at the N position, the dimethyl group is present. If the higher alkyl group is present, then it will rapidly decrease the activity. A cis and a cis ring and B ring fusion with the hydroxyl group at the 12th position. At the 12th position, okay. 12th position here, different R1 and R2 substitution I have shown you in the first slides. So 12 hydroxy position, if esters are formed, then it becomes the inactive drug, with the exception of the formal ester, which rapidly hydrolyzes in the aqueous solution. That means they will form a ester too fast because it will hydrolyzed by the aqueous solution. Alkylation at the C11 position, at the C11 position, the C11 position, if there is alkylation, that will also lead to the inactive compound. That means whatever the structure is given, if there is some slightest modification, the structure will be changing and the activity will be changing. Like this also dehydrogenation to form a double bond between C5A. So at at the C5 position, if this dehydrogenation is there, that means hydrogen is removed. There will be a formation of double bond between 5A and C11. See, I can see here at the C5 and C11. As a result, as does aromatization of the ring to form anhydrotetracyclines that will produce another compound. Substitution at the position of the 5A, 6, 7, 8, and 9 represent that's been in this position 5A, 6, 7, 8, 9, representing the largely hydrophobic northern and western faces of the molecule. So that means if this position 5, 6, 7, 8, and 9 positions are largely hydrophobic structure is substituted, northern and western faces of the molecule can be modified with the varying degree of success, resulting in retention and sometimes improvement of antibiotic activity. At the 5 position hydroxyl group is in oxytetracycline and doxycycline may influence pharmacokinetic property but does not change antimicrobial property. Okay. So acetable 6-deoxytetracycline and 6-dimethyl deoxytetracycline have been used to prepare various monosubstituted and disubstituted derivatives by electrophile substitution reaction at the C7 and C9 of the reading. That means at the 6th position, if the deoxytetracycline or dimethyl deoxycycline have been used to prepare these various many substitution of the disubstituted derivative by electrophile substitution at the C7 and C9 position. So at the C7 and C9 position, if there is different electrolytic substitution, there will be formation of the different drugs. The more useful results have been achieved with the introduction of substitution C7 or strongly electron withdrawing group, that is chloro, and a strongly electron donating group, that is dimethylamino minocycline enhance the activity. That means strong electron withdrawing group will help the chloro and nitro, and strongly electron group like dimethylamino enhance the activity. Okay, some of the electron withdrawing group and some of the electron donating will enhance the activity of the drug. The most fruitful site for the semisynthetic modification of tetracycline has been the R6 position, neither the 6-alpha methyl or 6-hydroxyl group as essential for antibacterial activity. But neither the 6-alpha methyl or 6-alpha hydroxyl group is essential. मतलब 6-alpha methyl group and 6-alpha hydroxyl group will be having very good antibacterial activities, essential for the antibacterial activity. Polar substituent at hydroxyl group at C5 and C6 decreases lipid versus water solubility of the tetracycline. The 6th position is, however, considerably more sensitive than 5 position to this effect. Non-polar substituents have the opposite effect. Now different products are there: tetracycline, polytetracycline, oxytetracycline, methacycline. So depending upon the different substitution, these drugs are produced. The tetracycline drug has become the most popular antibiotic of this group, largely because its plasma concentration appears to be higher and much enduring than that of the other tetracycline or oxytetracycline, chlorotetracycline. That means this oxytetracycline is in the plasma concentration have become the higher activity than the other tetracyclines. See the structure: polytetracycline, chlorotetracycline, okay, oxytetracycline, and different methacycline. The greater the stability of the methacycline, both the in vivo and in vitro, results from the modification of the C6. Removal of the 6-hydroxy group markedly increases the stability of the ring C to both acid and bases, preventing the formation of the isotetracycline by bases. So that means the in vivo and in vitro cases, if the C6 position is modified, that means removal of the 6-hydroxy group markedly increases the stability of the ring C to both acid and bases. That means if you remove the hydroxy group, it will be stable, the acid and bases, and preventing the interaction of the isotetracycline by bases also. That means in the C position, if the hydroxy group is replaced, then it will markedly increase the stability of the CD of the both acid. So preventing the formation of the isotetracycline at the base will be easier. See the structure of the doxycycline. The most importantly used. More recent addition to the tetracycline are tetracycline group of antibiotic available for antibacterial therapy. Doxycycline, alpha 6 deoxy, 5 oxytetracycline, fibramycin. At the 6th position, deoxy, hydroxyl. The 6 alpha methyl epimer is more than 3 times as active as its betamer. At the 6 alpha methyl group 6 position, this epimer is more than 3 times active as beta epimer. That means at the alpha position, the epimer methyl substitution is much activity than the beta. Apparently, the difference in the orientation of the methyl groups, which slightly affects the shape of the molecules, causes a substantial difference in the biological effect. So that means apparently the difference in the orientation of methyl groups, which slightly affect the shape of the molecule, causes substantial difference in the biological effect. That means if the methyl group is orientation is slightly somewhat different, like the below the plane or above, then it will affect the shape of the molecule slightly, but it will have a substantial difference in the biological effect. Either they will be decreased or increased, or they will be stable or unstable. So absence of 6-hydroxy group produces a compound that is very stable in acid and bases that has a long biological life. That means in this doxycycline, at this uh, at this 6th position, if it is 6-hydroxy group is removed, then it will produce longer biological life. In addition, it gets absorbed very slowly from the GI tract, thus allowing a smaller dose to be administered. That I was discussing about this. If the removal of the 6-hydroxy group make it markedly increase the biological activity to both acids and preventing the formation to isotetracycline also. Okay. So doxycycline I have already discussed. So as a result, what can I say? These are the total tetracycline structure. They are different nomenclature. And lastly, one slide is remaining, that is a newer tetracycline after the doxycycline. In addition, it is observed very well from the GI tract, thus allowing a smaller dose to be administered. That means doxycycline, if the 6-hydroxy group is removed, then it is very stable and it is very well absorbed from the GI tract. Now coming to the newer tetracycline, substituted in the aromatic reading in an effort to discover analogs that might be effective against resistant strains. Glycosyl cyclines, glycyl cyclines, place of 9-dimethyl glycylamine substituted tetracycline and discovered. The first of these two marked where was diglycycline. That means in the aromatic group, if it is substituted with another newer molecule, 6-dimethyl glycylamine, that is 6-DMG, substituted tetracycline are discovered. The first of these two markers is tetracycline. That means this tetracycline, if it is replaced with like C-11a and another substitution is there, then it is known as the triglycycline. So these are the different newer drugs. So up to this, I'm completing the structure of the tetracycline and the chapter of the tetracycline and also unit 1. Thank you.